every element exhibits some specific set of properties, usually determined by the number of electrons in its atoms and the distribution of those electrons around the nucleus. Also, every piece of a pure element exactly exhibit the same properties regardless of its size. A piece of pure gold, for example, has properties that is very different from a piece of pure silver or any other pure element like pure copper or pure aluminium. But every piece of gold, whether it is large 100-gram piece or small 10 milligram one, has exactly the same properties. This is one fundamental fact of the chemistry. But about 40 years ago, scientists started discovering something very remarkable. Very small particles in the nanoscale range were found to behave slightly different way than the larger particles of the same element. A nanoparticle sizes in the range of 1 to 100 billionth of a meter of gold, for example, displayed properties different in some respect from larger particles of gold. Such deviant behavior had been predicted in theory a few decades earlier, but never observed. So, today I am going to discuss with the Chemistry Nobel of 2023 awarded by Royal Swedish Academy. So, the 2023 Nobel Prize in Chemistry is awarded for the experimental discovery of quantum dots, which are nanoparticles made of a semiconductor material. Nanoparticles are extremely small particles of various substance that are on the order of 10 to the power minus 9 meter or 1 billionth of a meter in size. To try to understand how small that is, we can compare with the head of a pin. A nanoparticle is about a million times smaller than that. The laureates have been pioneers in the exploration of the nano world, and their work has been pivotal in the development of nanotechnology. Among other uses, quantum dots have given us new ways of creating colored light. So, these are the pictures of Nobel laureates of 2023 in chemistry. Mongi G. Barwendi, who was born in 1961 in France, much later than Louis E. Bruce, who was born in 1943 in USA, and Ekimov, Mr. Ekimov or Dr. Ekimov, who was born in 1945, that is the former Soviet Russia. Alexei Ekimov was the first to notice this deviant behavior in copper chloride nanoparticles around 1980. He was also able to manufacture these nanoparticles to show this change in behavior. A few years later, Louis Bruce, an American scientist working independently, discovered similar behavior in cadmium sulfide nanoparticles. He too was able to create these nanoparticles with changed properties. Mongi Bawendi, who worked with Bruce in the initial part of his career, later developed easier methods to efficiently produce nanoparticles that showed some desired deviant behavior. So, what is quantum dot? A quantum dot is a really small assembly of atoms, just a few thousand, around a few nanometers wide. Nanometer means 10 to the power minus 9 meter. You could fit as many as quantum dots inside a football as you could fit footballs inside the earth. Okay, so this is the level of comparison which you can do or you can make. The quantum in its name comes from the fact that the electrons in these atoms have a very little space to move around. So the crystal as a whole displays the quirky effects of quantum mechanics. Effects that otherwise would be hard to see without more sophisticated instruments. Quantum dots have also been called artificial atoms because the dots as a whole behaves like an atom in some circumstances. Okay. The deviant behavior of small nanoparticles arises because of the emergence of quantum effects. The motion and behavior of very small particles like electrons are radically different and strange when compared with any familiar object in normal human experience. Sorry. Such strange behavior at the subatomic level is described by the hugely successful quantum theory developed by physicists around 100 years ago. But nanoparticles are much larger compared to the atoms also. Depending on the size of atom, a nanoparticle can pack thousands to millions of atoms in itself. However, it was theorized in 1930s itself that when the size of particles was reduced to nanoscale, it could give rise to quantum effects. Okay. So, what gives rise to this quantum effect? This was mainly because electrons were constrained in a small space. Okay. Usually electrons move around a large empty space, relatively speaking, outside the nucleus of the atom. But when the size of particles is reduced drastically, electrons in the atoms find themselves increasingly squeezed conditions. And this, it was thought, could give rise to the strange quantum effects in the nano level. Okay. This is what Ekimov and Bruce noticed. And this is what they were able to create in their laboratories. Nano-sized particles that behaved slightly differently than larger particles of the same element. Okay. So, one of the most noticeable spatial properties of the nanoparticles becomes evident when they interact with light. The color of any material depends on the wavelengths of light spectrum absorbed or reflected by that material. When the light is shined on quantum dot, it absorbs and then re-emits it at a different frequency. Similarly, smaller dots emit bluer light and larger dots emit redder light. Okay, this happens because light shown on the dot energizes some electrons to jump from one energy level to a higher one before jumping back to down and releasing the energy at a different frequency. So quantum dots can be easily adapted for a variety of applications, including surgical oncology, means in cancer treatment, advanced electronics, and even quantum computing. So let's discuss the Ekimov's works. Okay, who was born in USSR. Ekimov was working with colored glass tinted with copper chloride when he noticed something special. He heated molten glass to very high temperatures and then allowed it to cool and harden. Crystals of copper chloride of different size had formed on the glass. He observed that the part of the glass where smaller crystals of copper chloride were present had a slightly different color than the area where there were larger crystals. Okay. What this showed was that the same material, copper chloride, was absorbing different wavelengths of light depending on the size of the crystal. Okay. Now let's discuss the works of Bruce. In 1983, a group led by Louis Bruce in the US succeeded in making quantum dots in a liquid, rather than trapped within glass as Dr. Ekimov has done or had done. Bruce too realized that particles of different sizes, all in the nanometer range, were interacting with light in different ways. This meant that apart from the number of electrons, the properties of material were also being dictated by its size also. Both Dr. Bruce and Dr. Ekimov further studied quantum dots, working out mathematical description of their behavior and how it related to their structure. But both of them lacked one thing. Their methods required extreme conditions and produced particles of unpredictable quality. That is, they are not getting that quality of which they are interested about. Okay. Then comes Bawendi. A team led by this person at MIT achieved this in 1993 with hot injection method. A reagent is injected into a carefully chosen solvent having a high boiling point until it is saturated and heated until the growth temperature, that is when the reagent's atoms clump together to form nanocrystal in the solution. Large crystals form if the solution is heated for longer. Their birth within a liquid makes their surface smooth. Finally, crystal of the desired size can be simply filtered out. This method accelerated the adoption of quantum dots in a variety of technology. The quantum dots Bawendi produced were practically perfect, unlike the imperfect nature of the other two people's work, and gave rise to very clear quantum effects. In addition, his manufacturing methods were inexpensive and simpler to use, unlike the other two people's experiments. So, what are the applications of quantum dots? An array of quantum dots can be a TV screen by receiving electric signals and emitting light of different colors. Scientists can control the path of chemical reaction by placing some quantum dots in the mix and making them release electrons by shining light on them. If one of the energy levels an electron jumps between in a quantum dot atom is the conduction band, the atom can operate like a semiconductor. The solar cells made with quantum dots are expected to have thermodynamic efficiency as high as 66%. A quantum dot can also highlight a tumor that a surgeon needs to remove. Hasten chemical reactions that extract hydrogen from water, that is electrolysis of water, and as multiplexer in telecommunications. So this was my discussion for the day. Thank you for watching the session. Keep yourself mentally and physically fit. Bye bye.